Hi, welcome back. So today I'd like to talk a little bit about working with strings, and I've created a blank stub file, and I'd like to go ahead and save this. And we've worked with strings a little bit before. We could, build off the same file that we had before. I'm just going to create a new folder and call it something like string2. And then let's have a main.go file inside there since we're going to be running code here. So what I'd first like to talk about is, let's give kind of a motivating problem, something that we want to solve. And I'm going to put this in a multi-line comment. So I want to formulate a computational problem that we're going to solve, and let's call it the pattern counting problem. And this is just to count the number of times that a pattern, i.e. a string, appears in a longer string or text. Okay, so our inputs here would be a strings pattern and text, and the output, and I might switch these actually, text and pattern, and the output is simply going to be the number of times that pattern appears as a substring of text. Okay, now this is a straightforward problem, and in fact there is a built-in function in a package called strings that will count the number of times that a pattern appears in a larger text. So if I import strings, and then for example I call strings.C count, and we have something like let's have a text of banana, and let's have a pattern of AN. Okay, so that should occur 2 times in that text, and let's save, and then let's go to the console and navigate into our directory. So let's navigate into go src, and we called it string2, and then let's go run main.go. Okay, and so we're going to see that 2 gets printed. So it doesn't seem like we really need to implement anything here, but let's see what happens if, for example, I give it another example where we have something like, and this is a relevant example to DNA, where we want to count, say, the occurrences of ATA, and let's count the occurrences of ATA in the string. Let's say CG, ATA, TA, GG, ATA, C, something like that. And you'll see that here, ATA occurs here, here, but it also occurs as an overlapping occurrence here. So these 2 occurrences overlap. And what you'll see is that when you save this, if we run the program again, we would expect for this second printed value to be 3, but in fact it's 2. So the lesson is that strings.count doesn't account for overlapping occurrences of pattern in text. So we'll need to write our own function if that's what we want to model. And I'll say including overlapping occurrences to specify that in our computational problem. And so let's write that function ourselves. And to get at that, I kind of want to introduce, a couple of short notes about how to work with strings. So, for example, we may recall from a previous lecture that if you print, say, hello plus there, then the plus symbol, which normally is treated as addition of numeric variables, in the strings world simply concatenates the 2 strings together. So the string hello there, all one word, gets printed. If we wanted to add some space, we could simply add a space symbol there, and when we printed it, everything would be fine. Okay, so the next thing I would note would be strings have a fixed length, so they work like arrays in some ways, which is that once you declare a string like hi there exclamation mark, then it has a fixed length. So you can say print the length of S is length of S. Okay, so we can run our code. The length of S is 9, and that's simply the number of symbols, 4, 5, 6, 7, including the space, 8, 9, okay, in the string. We could also print something like the first symbol of S is, and I mentioned in a previous video that strings are essentially can be viewed as arrays of bytes or arrays of symbols. They're not the exact same thing, but we can use indexing in this way to say the first symbol of S is, and when we run main.go, we see that again, the first symbol of S is the number 72. So if we wanted to print that as a string, we could simply call that. Okay, and then when we run main.go, forgot to save, the first symbol of S is H. Okay, and we see that that's there. The other thing is we could do, say, the last symbol. And just as with arrays, the indexing is going to run from 0 to the length of the string minus 1. Okay, so when we save, go run again, the last symbol of S is the exclamation mark, which we know to be true. We could also say if S of 1 is equal to, and we could do a test. So we could test based off of a single symbol of S. So if that is equal to, say, E, which we know to be the case, we can test, is this equal to the symbol E? And Go is viewing that internally as a number, but it's okay to call it, in single quotes, the symbol E. Let's print second symbol is E. Okay? And so we save, and that test should get executed, which it, oh, well, I thought it was hello there, but it's hi there. I wonder why it didn't get executed. So it didn't get executed. Second symbol is E, okay, and so on. So substrings is the next thing I would talk about. You can access an individual symbol, and that's going to be as a byte character. You can access a substring of a longer string. So we might print, say, everything in S from 3 to 5. Okay, and the question would be, what do you think might be printed there? And there are a few possibilities. If you think it's probably the third symbol to something else, so you might think, well, what's the 0th, the first, the second? So we might think third, fourth, fifth. Okay, so we might think that THE is printed. That would be a reasonable thing. When we run it, we actually see that what gets printed is just the TH. And there's good reason for this, which is because we can easily get the length of the substring by simply subtracting the top index minus the bottom index. Okay, so just as we start indexing at 0 and go up to the length of the string minus 1, we start indexing a substring at the index that we're interested in and go up to the highest element, but not including that element. Okay, so this would give us the third and the fourth element, but not the fifth. And again, it makes things easy to know immediately how long that substring is by simply subtracting 5 minus 3. So you can, another way of thinking this is that this is the substring starting at index 3 that has length 5 minus 3 or 2. Okay, if we omit the second index, then it treats it as if we had done length of S there. So that would go up to the length of S, but not including length of S, which would be good. So when we run that, 1, we get everything starting with the first position, which is I, and then going up to the end of the string. We can omit that and get the same result. Okay? If you omit the first index, then it treats it as if it were a 0. So if we go 0 to 4, then we're going to get the substring of length 4 that starts at position 0, which is high space T, as shown there. And so if we omit that first index, we get high space T again. And then we could introduce, say, substring is equal to S of 3 to 6. And then we could print substring and see that it's going to be a new string starting at position 3 of length 6 minus 3, which is 3, which is just the string the. So, and we can work with that however we like as well. Okay. And that would give us 101, which is a symbol. If we wanted to know what that symbol actually is, we could convert it to a string. And I forgot to close. And that symbol is an E. Okay? So those are the basics of string manipulations, concatenation, taking substrings, and so on. Another useful strings function is contains. Okay, and that returns a Boolean. And I encourage you to go and take a look at the strings package and look at the types of functions that are built in. But for example, I could test if hi there contains the string the, which is true. And what that function returns is true in that case. So if I run our code, I forgot to do strings dot contains. It's lowercase strings. Hi there, and the. So it is true that the occurs in hi there. So you can imagine you might have a test. Does this substring occur anywhere within the longer string? Something like thx, it's going to return false in that case. Okay, so we have that built in for us. And now we can return back to, now that we know the basics of string manipulations, we should be able to return back to our pattern counting problem, where we wanted to input strings, text, and pattern, and we wanted to output the number of times the pattern appears as a substring of text, including overlaps. So I'll leave this to you as an exercise, and I'll just write the function signature, so the first line, or the overall arching description of the function. So we could have, and let's call it count pattern, and let's give it a text and a pattern as strings, and we're going to return an integer. You could return an unsigned integer as well. I'm just going to return an integer here. So take a second and think through how you would use what we've learned here to write this function. And I'll assume that you've paused and have taken a chance, and I'll just continue on and show you this function now. So what we need to do is we need to range over. So range over the text and essentially slide a window. And this is going to handle the overlaps. So if we look at what we had before, we need to first consider the window starting at position 0, having length equal to the length of the pattern. And then we slide the window over again and compare, over again and compare, and over again and compare, and so on. Before, if the ATA is detected, then strings.count is jumping to the next position. So that's why it's not picking this up. And we need a different way of indexing the string that slides and then only moves the window over by 1. So the way to do this is to say, well, let's declare a count variable, and that's the variable that we're going to return later. So we're going to constantly increment count as soon as we see a pattern match. So I could say, as a comment, range over the text. I should say a sliding window over the text, incrementing count whenever we see pattern. So we're going to need a for loop. And then the question is, well, definitely the for loop should start at the first starting position, and then it should go up to something. It would be easy to do it up to the length of the text, I++. And so that's our ranging. But we have to keep in mind a couple of things. First, well, what we need to keep in mind is that we will have a starting position here, but we won't actually have a starting position there or there. So we don't want to range over all possible starting positions. We want to acknowledge that we're eventually going to hit the end. Okay, and then the question becomes, well, what is the end? You may want to pause and take a second to think about how we'll know. We'll be able to have something here that's a test for knowing when we've hit the end of the string. For now, I'll say, let's make things a little bit easier on us. Let's declare a couple of intermediate variables. So I like, here let's declare n to be the length of text and k to be the length of pattern, so that I don't have to constantly keep calling length of text and length of pattern if we use them. And if you compare this, try this for a couple of examples, what you'll see is that this is starting position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The last starting position that we want to encounter is 10, and the string ends at position 12. If we added a symbol there, right, then we would end at one more early, right? So it would be we would stop at starting position 9. So the length of this string is 12. So if the length of the pattern is 3, we stop at 10. If the length of the pattern is 4, we stop at 9, and so on. And you're going to see that the last starting position, therefore, is n, the length of the text, minus the length of the pattern plus 1. So for this example, we have string of length 12, text of length 12, pattern of length 3, and the last starting position is at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that would be 10 minus 12 minus the length of the text, 12, minus 3 plus 1. Okay, so we do n minus k plus 1, and then we slide the window. So at each window, we now need to compare substring of length k at position I of text to pattern. So we're matching them up, and if we see a match, then we're going to increment count. So we say if pattern, and now we can test string equality just using the equal sign, double equals. So if pattern is equal to the substring of text, okay, so now we use our substring notation, the substring of text, and we say it starts at position I, and it has length k. Well, we say what here, when we subtract this number, minus I, will we get k? And the answer is just I plus k. So a pattern is equal to text of I to I plus k. Then we simply increment count, and now we're done. So we'll return count at the end. And I'm going to, just for the time being, at least comment out a lot of the basics of string manipulation, so we don't have quite so much printed. And I'm going to compare not strings.count, but count pattern, that function that we wrote, on the same two strings as a test, because now we should be able to actually get 3. So when I save, run, I had a slice bound out of range, and that's because we went too far. So the length of the text is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I was off by 1. I knew I was off by 1. So its starting position 10 is n minus k. So we go up to n minus k. So we have n minus k. It's so easy to be off by 1. We have n minus k plus 1 total positions. We start at 0 and we end at n minus k inclusively. So I could have fixed that by just having I less than n minus k plus 1, but instead we do I less than or equal to n minus k. Either one works. Now when we run, we're going to get 3 as our value instead of 2. So I'll leave that in just because it's useful to see that off by 1 errors are common. And I should have known that was going to happen in advance, but that's okay. And we can do another test, which is just banana, N-A-N, and that should be 2. So when we save and run, we'll see a 2 down there again. Okay, so all's working there. Let me give you an exercise. So let me give you, and I'll move it down below, count pattern. Let's do a reverse complement problem. So this is motivated by the fact that DNA has 2 strands, and find the reverse complement of a DNA string. So the 2 strands run in opposite directions, and opposite directions, A always bonds with T, G always bonds with C. So our input's going to be a DNA string text, and the output is going to be the reverse complement of text. And so as a result, for example, the reverse complement of, say, the string ACTAG, okay, is, well, we start at the end and reverse and then take the complementary nucleotide. So we start at the end, the complementary nucleotide of G is C, then the complement of A is T, complement of T is A, complement of C is G, complement of A is T. So that's the reverse complement of ACTAG. And I want you to think for a second, if we were thinking top down, what might we do here to solve this problem, to make our job kind of as easy as possible on ourselves? So take this second and think about that. And I'll show you in the meantime that if we wanted to write a function called reverse complement that took a string as input and that returns a string, then we could think about doing this entire process, ranging through the string backwards and then adding nucleotides to a new string based off the complementarity, and we'd wind up with a long function pretty quickly. But if we're really thinking top down, we'll notice that the idea of reverse complementing a string splits into 2 completely separate tasks. One is reversing the string, and the other is taking the complement of each nucleotide. So if we take the complement of each nucleotide in a given string, and then as a separate task, reverse it, then we're going to get the exact same result. So the clever thing to do here is to return the reverse of the complement of S. And what I mean by that is that we're going to now have 2 functions. We're going to have a function called reverse that takes a string S and returns a string S. And we're going to have a function called complement that takes a string S and returns a string. Okay? So we could say reverse takes a string as input and returns its reverse as output. Complement takes a string as input and returns the string formed by complementing every nucleotide, e.g. A goes with T and C goes with G. Okay, and this, we need to be careful here because it doesn't take an arbitrary, it's going to take an arbitrary string, but it takes a DNA string. So if we're really focusing on style, we're going to need to make sure that we handle cases where the user inputs something that's not a DNA string. So the string has like a Q in it, for example, because we don't want our code to break in those cases. It's very important that you do that as part of programming. I'll leave that to you at the end to kind of fill in the blanks there and use something like os.exit or panic and provide feedback to the user, and then test your code to make sure that everything is working only on strings with A's, C's, G's, and T's in it. For now, let's focus on writing each of these individual functions. So we could do, say, complement first. And one of the things that we could do here would be to say, actually the first thing I want to do is I want to provide placeholders here and save and just go build to make sure our code is still compiling. As long as you then know to get rid of this, it's good to know that you've declared everything all right, everything has the right types and so on. So you're ready to go, and everything, any new issues are going to arise. Any compiler errors that you get from now on are things that you've coded since that point. All right. So let's focus on the complement function. And how I'd like to do this would be, in an ideal world, let's say, let's change the symbols of S. So let's have for I colon equal to 0, I ranging over the length of S and incrementing I. And as we range over S, let's have, say, we could do an if statement, but here's a good example of where a switch statement can be helpful. So we could range over S of I, or range over S, and at S of I test, is it an A? Well, if it's an A, S of I is equal to T. Okay, so we could update the ith element of S to be equal to T. And then we have the other cases. Don't know why the indentation is doing that, but we could have the other cases. S of I is equal to G if we see a C. If we see a G, then S of I is equal to C. If we see a T, S of I is equal to A, okay? And at the end, and then maybe we would have a default where where we would panic and say something like string passed to complement isn't DNA. Okay, and I'm just going to go fmt main.go and it's going to get everything nice and pretty for us. Okay, so that's a good usage of the FMT function in Go that's going to allow us to format our code nicely for us, where it actually adds these S of I's on new lines. Okay, there's nothing wrong with putting them on the same line, but this makes it super readable. All right, so that handles the case where you pass in something that's not an A, C, G, or T. You could do lowercase letters as well, but that's going to be a really long switch statement. And so at the end, we want to return S. Okay, and now let's see what happens if we try to call this. So I'll comment out everything but the new things that we're going to use. And so let's try to print the result of complementing. Let's say, well, we'll use our example. So our example was ACTAG. So this shouldn't reverse the string, it's just going to complement things. Okay, and now when we run, we get an issue, all right? And the issue is that, well, one is we don't need strings anymore. But if we look at the feedback that we get, we're missing the return at the end of the function on line 42. Okay, so that's acceptable. And the main issues that we're getting are the other things. Cannot assign to S of I. Okay, so we get an error here, which is that strings are not editable in the sense that once you have a string fixed, you can't change a single symbol of S in this way by assigning S of I equals to some other symbol. So instead, we'll need to think about a different way of doing this. And instead, rather than changing the string S, that's okay. I'm just going to define a new string to be, say, an empty string. And then as we go through, we're going to still range over S, okay? But now when we see an A, rather than appending to S, we're going to append to S2, and S2 is going to be what we return. So let's do plus equals, because we're going to be concatenating this string as we go. And now we should be good to go. So now let's see what happens when we go run it. And we're going to get another issue, which is that we cannot assign to S2 of I. The issue this time is that String concatenation works by concatenating two strings. So this is the same as, and I should say, sorry, I jumped ahead of myself. S2 should be plus equal. So this is saying S2 is equal to S2 plus the symbol T. And when we go run, we're going to get a different compiler error, which is the one that I wanted, which says there are mismatched types string and rune. So rune is also a character symbol. So because they're mismatched, it means that you cannot concatenate a string with a symbol. So here, this is actually an easy fix. This is S2 equals S2 plus the symbol T. It wants to see if we're concatenating two strings, they should be strings. So we need to give it double quotes, and that's the only fix that we need. So we give it a double quote to indicate it's a string literal and not a symbol literal. So when we save that and run it, we're missing our return at this function. And let's run this so that we can test it. And we get that the complement of ACTAG is TGATC. So all looks good there, okay? Now we just need to write the reverse function, okay? So I'll leave this to you as an exercise. Feel free, I think you've learned enough to be able to try and write this function, replace the return S that we had before with a function that's going to take S and return a new string, let's say S2, formed by reversing all the symbols in S. So take a second and try that out. I'll continue on. What we need to do to reverse a string is, let's do S2 is an empty string. That's eventually what we're going to return. Let's say for I colon equal to 0. So we need to range through S, I less than the length of S, and increment I each time. Well, we need to append to S, and then the question is, we're ranging through S, and then we need to append the thing that is at the corresponding position at the end. So at position 0, we're going to append the length of S position, the symbol at position S, length of S minus 1. Okay, so the first symbol of S2 is going to be the last symbol of S. I should say the 0th. The symbol at position 1 of S2 is going to be the symbol at position length of S minus 2. The symbol at position 3 is going to be length of S, the symbol at position length of S minus 3, and so on. So you can see that there's a pattern there, and the pattern is simply, let's go into S and grab whatever is at the length of S minus I minus 1, right? Because when I is 0, we want length of S minus 1. I probably should write it that way. That might be a little bit clearer. When I is 1, we want to pick the symbol in S at length of S minus 2. So that's minus 1 minus another 1. When I is 2, we want to pick length of S minus 3. So that's minus 1 minus 2, and so on. And it's very easy to write it in this way and then forget that, in fact, that's a symbol. And if we're concatenating strings, we need to have a string. So we can simply do a typecast where we say string of that. And now we return S2, and we should be good to go. So short function for reversing a string. And now you see the power of top-down programming and splitting, modularizing this into two functions that we can test independently as well. One's a complement function, the other is a reverse function. So now we should be able to test the reverse function as well. And save and run. And the reverse of ACTAG is GATCA. It'd be very easy to have an off by 1 error there and wind up with either an out of range error where you went too far, you ranged up to like length of S instead of length of S minus 1, or you tried to access a string index that wasn't there because you were off by 1, or you wound up with a string of length 4 here because you didn't quite do every single symbol, you did everything but 1. These are very common errors and the types of things to look out for when you start working with arrays and strings, to make sure that you're actually hitting every single index and you're not off by 1 that would leave you short or too long by 1. The point here is that we've tested our reverse function, we've tested our complement function, so now we should feel pretty good that if we test our reverse complement function, and we run it, then we should get, well, C, T, A, G, T. C, T, A, G, T. And everything appears to be working there. So good news there. We've got a function there that's working. And that's largely all I'll say for today. There's just one more thing that I wanted to point out, which is that this notation, for I colon equals 0, up to the length of S, so where S is either a string or an array, and then incrementing I by 1 each time. I used the word ranging, I believe, like ranging a sliding window over the text, or ranging over the text. And this is such a common setup to have a for loop that starts at the starting position, ends at the final position, increasing by 1 each time over a string or an array, that Go has shorthand here called range. So instead of all that, we can just do for I colon equal range of S, and I could say for I colon equal range of S is equivalent to for I colon equal to 0, I less than length of S, I plus plus, and you'll wind up using that a lot as you get more comfortable programming in Go. There's just one thing that I'll point out, however, which is that you want to be very careful that you're using this in the appropriate contexts. So for example, remember for count pattern, it would be very easy to replace this with for I colon equal range of S, or range of text in this case. But in that case, remember, we didn't want to consider every single possible starting position in the text. We wanted to consider every starting position that would result in a substring of length pattern. So we didn't want to go all the way too far out, otherwise we got an index out of bounds runtime error. And so for here, it would be very tempting to use range, but you need to keep in mind knowing when that range is only equivalent to when we truly range over every single starting position of the text. So that's it for strings. Thanks for joining me. I'll see you next time.